Okay, so I think we're going to make one or two videos about derivatives. So we always have the book open here, but obviously I use the book as a whiteboard. So they kind of have their brief, kind of long drawn out explanation about derivatives. Um, I could actually derive the definition of the derivative. I've kind of done a little graph, a little illustration, and then I just wrote the definition of the derivative right there. So specifically, this right here is the definition of the derivative. We don't need this for this class. It's just, it literally is the definition of the derivative. I wanted to say really quick, as we all know, we have all the derivative formulas, a whole list from very easy to very hard. I've derived some of them. The kind of the derivation is not that easy for a lot of them, but where do the derivative formulas come from? All derivative formulas, all of them are derived from this. They're all proven from this one formula here that we didn't like so much in Calc 1, the definition of the derivative, the limit, bottom of the fraction to zero. Like I said, the more I talk, we're not going to derive the whole thing. It would take like at least a 10-minute video, probably more. This looks different. Limit, delta x to zero, uh, delta y over delta x, but it's not. Delta y is this entire thing in the numerator, and h is the delta x. So those are actually the same two statements right there. So I just wanted to state the definition of the derivative. We don't need that. We just want to say one thing. I did say this in a previous video. We're just going to cover it again really quick. So if we state the derivative, what is the derivative? So if you have a function f, yeah, over here we have a function f. If we have a function, f of x, if you take the derivative is the formula for the slope. We can talk about it for a second, or we can, read 2 pages on it. The only thing we're getting at is that if you take the derivative of the function, what the derivative is the slope of the function. If you have a y equals mx plus b, we're kind of done with all this. All of this I'm going to end up repeating again. But if we have a y equals mx plus b, which is a straight line, if you take the derivative y prime, it equals m. So it equals a constant because the slope of a straight line, rise over run, is the same everywhere. Yeah. All we need is a basic parabola, yeah? It doesn't really have to be y equals 2x squared, but why not? But y prime equals 4x, which of course is an equation, yes? So why is the slope going to be an equation? We don't write it that way, but m, the slope, could equal 4x. That's not 4x. Could equal 4x. The reason for that, yes, is because the each point has a tangent line which traces the slope. This is where the slope is 0. Each point of a curve, infinitely many points, therefore infinitely many slopes. Each point on the curve has its own slope. Therefore, the derivative would find the slope at that point. So we need not say any more. If I talk about this entire section, which I'm going to right now, we are only making that one point. So once again, I said in another video, we could just memorize it. We don't even have to understand it. It's going to come time and time in this book. But the main, most fundamental in econ, micro econ, and in economics, yeah, the derivative f prime of x is a marginal change, and we have that weird little annoying concept. Hold on. Yeah, marginal change. We really, really like the derivative calculus and the derivative in math because it's not an average change. It is the instantaneous rate of change. I can never say it exactly. Yes, the derivative, I should have said it a moment ago, but the derivative is the slope, and it is, we know that. And the slope is a rate of change. Apologies if I say it like 10 times in a row because I know we did all of this in a previous video. Yes, but the derivative is the slope, is the rate of change, rise over run. Okay, they're all the same thing. Instantaneous, yes, instantaneous. Yeah, the reason why we like the derivative so much is because it's the instantaneous rate of change at any x or any moment in time. Let me write that again. So in economics, yeah, in econ, we have this marginal change. Yes, we have this marginal change. We have this thing that's kind of annoying because, like we just said, instantaneous, yeah. Um, this is the slope is going to be the rate of change. The slope is the rate of change. So if you have a small, that's going to be a small delta x. If you have a very small change in x, the slope, the rate of change has already changed. So that's the annoying thing, is that if you go just a little bit to the right, yes, the slope has already changed. Yes, but if the slope has not changed that much, then the slope can kind of be thought of as constant. So what we use the derivative for at the most fundamental level, introductory, what we use the derivative for in economics is to calculate marginal changes. Very, very, what is the change in y going to be if you have a very small change in x? Uh, we have to go on because I'll get off subject, but they're going to do elasticity too really quick here. Yes, but in econ, the derivative is the marginal change, which is just the change in y for a very small change in x under the assumption that the slope doesn't change that much because that is the derivative. Yes, but I don't think we need this chapter too much because it's all a little bit too easy. So throughout this book, we will see the optimal economic decisions are made by looking at how marginal changes in X affect Y. When we look at marginal changes, we're simply looking at the derivative of the function f. Recall from your calculus class that a derivative of a function of one variable is simply the slope of the tangent to the graph of the function f at some point. We will use notation, that's just the derivative notation, one of many, to represent the derivative of a single variable function f with respect to x. We may also use the denotation. We like both of those right there. So we see the two notations at the top of the page, yeah. So the function y equals 4x has constant slope. They do kind of a picture right there. We could kind of read all of this, but in my opinion, if we kind of go through all of this, figure 2.1, 2.3, all of that, we just go very, very carefully through this. All they're telling us is the three. I call them the three. The derivative is the slope, is the rate of change. And we do really, really like it in calculus because it's the instantaneous rate of change. Yeah. So we see with B there. Yeah. Okay, so with B, the tangent line is the slope at that point. The tangent line is the slope. Yes. Okay, so here, I think we're going to skip this. I can actually derive the product rule, quotient rule, and all of that. We're going to jump to some very, very basic homework. So it's kind of time to take a few derivatives. What did we say a moment ago with the definition of the derivative? We said that, we have the general power rule. If y equals x to the n, yeah, then y prime is going to be power out front x to the n minus 1. Very silly, we all know that. That's the power rule or the general power rule, the very first derivative that we all use. Yes. But what we have is we have the derivative formulas. Yeah, so we're going to do some very, very basic homework before we move on. This does not matter so much here. Yes, like all of this messy stuff we don't need to read. I can kind of mathematically show a quick proof of the product rule, chain rule, and quotient rule, but we don't need to prove all of that here. Let's see if we can clear that. Okay, so if we kind of take a look here, yes. And then right here on page 11, pretty soon after homework, we're going to jump right into where we need to be, which is the multivariable functions. So we will cover that soon there.